Hello and welcome to our webinar on Accelerating Portfolio Level Analysis with Third-Party Analytics, a Technology Perspective. I'd like to thank you for joining us today. My name is Carol Jansen and I will be moderating today's session. Before we begin, I'd like to cover a few housekeeping items. Today's webinar will last approximately 60 minutes. If you have any questions during the presentation, feel free to type them into the question box on the GoToWebinar toolbar on the right-hand side of your screen. We have set aside about 10 minutes for Q&A following the presentation, and we'll try to answer all your questions at that time. We will also be recording today's session, and you will receive a link to that recording in a follow-up email. Now I'd like to introduce today's speakers. Dr. Tony Webb is FinCAD's Director of Analytics. He has more than a decade of quant experience and holds an MBA with a specialization in finance and derivatives, as well as a PhD in computational fluid dynamics. Our second speaker is Dr. Mark Vlitos. He is FinCAD's Product Manager of Enterprise Solutions. He joined FinCAD in 2008 following 15 years of industry experience with various financial institutions in London, and he holds a PhD from King's College. New innovations in third-party analytics technology are enabling solutions for even the most complex, sizable, or changing portfolios to be built and managed efficiently. In today's webinar, Dr. Tony Webb and Dr. Mark Vlitos will provide their insight into the technology required for effective portfolio analysis. Utilizing a technical demonstration, they'll review best practices in calculating portfolio level metrics such as hedging factors, CVA, PFE, DV01, and aggregate risk, and will show how you can develop portfolio systems that are easy to maintain, extend, and to scale. And now, let me turn the webinar over to Tony.
Thanks, Carol. As Carol said, what we're talking about in this webinar is how you can efficiently produce a portfolio analysis solution that is easy to maintain, extend, and scale. Such a solution will, by its very nature, carry out portfolio-level analysis internally. What do we mean by portfolio-level analysis? Well, what we mean is any calculation that needs to be done at the portfolio level, as opposed to, for example, calculations done at the trade level. This distinction is important when the aggregation is not trivial. For example, aggregating the value is easily accomplished by summing the value of the individual positions in the portfolio. To calculate the value of the portfolio, you simply need to iterate through the positions within the portfolio, value each one, and sum them. In other words, f of p equals the sum of the individual f of ti. But as you will see on the next slide, there are some aggregations that are not so simple, and it's not necessarily true that f of p can easily be calculated from the individual values of f of ti. It all depends on the function f. Here are some other examples of analysis carried out at the portfolio level. In other words, these are different types of the function f. The total value we've already discussed. Aggregated cash flows. Well, you might need all of the future cash flows for a portfolio sorted in chronological order. Again, this aggregation is not difficult if the cash flows for each trade were available. It involves marshalling the data and applying a sort algorithm. However, it's a common operation that would be best delegated to a single implementation. So far, the aggregations have not been complicated and do not require sophisticated calculations at the portfolio level as long as it exists at the trade level. But as we proceed down the list, the aggregations are not so simple, and most require information about the risk factors that are shared by multiple positions within the portfolio. Risk sensitivity. This is the rate of change of the value of the portfolio with respect to the market data. Being able to calculate this first-order sensitivity is a vital component of any risk system. For example, it can be used to calculate DV01, which is the sensitivity of the portfolio value to a small shift in interest rates, a parallel shift of the whole yield curve. It can also be used to calculate hedge factors, which are the positions in liquid vanilla instruments that would be required to add to the portfolio to provide an instantaneous hedge of all market and credit risk. The fourth bullet is stress testing. This involves revaluing the portfolio under a number of different scenarios for the market data to quantify the exposure to more extreme market movements than are captured using first-order risk sensitivity. Credit value adjustment and potential future exposure are calculations performed on a set of trades with the same counterparty. CVA is an adjustment to the value of a portfolio to reflect the credit risk of the counterparty. PFE is a calculation of the maximum possible loss that would be realized if the counterparty were to default for a given confidence level such as 95%. The final example, value at risk, is the maximum possible loss over a given time horizon that is suffered as a result of market fluctuations, again for a given confidence level. It is a measure of market risk, whereas PFE is a measure of counterparty credit risk. There are many other examples of portfolio level analysis. So what makes a good portfolio analysis solution? At a high level, a portfolio analysis system should support better business decisions based on timely and accurate forecasts, even when historical data is scarce. It should provide the flexibility to rapidly assess the impact on the user's business resulting from changing market conditions. It should be cost-effective for both you, the developer, and your customers, the users. And it should provide risk analysis. This is certainly true for risk management systems, but even for solutions whose primary purpose is not risk management, it is often the case that risk parameters are required. So drilling into each one, better business decisions are only possible when up-to-date and timely information is available. The challenge is to provide tools that help your customers or your customers' customers gather the knowledge and insight needed to make more informed decisions. The ability to evaluate all possible outcomes, even if your customer only needs or wishes to analyze a small subset, is a key capability for any portfolio analysis solution. Decision makers need complete visibility into the inputs and analysis performed. All projected impacts on a portfolio should be fully quantified and available in multiple time frames and, where appropriate, currencies. Any aggregated report should allow the user to drill down into the details of how the rolled up values were derived. Transparency in how numbers are generated is critical in building confidence in the accuracy and reliability of those outputs. And finally, as I mentioned earlier, in order to make better business decisions, customers need timely reporting, often in real or near real time. With modern portfolio solutions, it is now possible for you or your customers to create new derivative products that have been brought to market without a single line of new software being written. It is possible for those new instruments to be integrated into existing trade processing and portfolio analysis systems as soon as they have been created. This level of flexibility is unprecedented and was, only a few years ago, thought unattainable. The advent of service-oriented architectures promised to make business services broadly available and reusable. The aim was to eliminate boundaries between business functions by making it possible to integrate the disparate and often legacy systems found in many customer sites. But a real-world SOA, not to forget the latest SOA in the cloud, can be challenging. Your customers' systems often span departments and geographies. Your portfolio analysis solution must integrate data sources and applications and provide visibility and business insight across many different platforms, both internally and externally. Not only does your system need to be fast, secure, and always available, You also want your solution to be extensible and capable of coping easily with the inevitability of a continually changing landscape. As a software developer, it's often tempting to build everything from scratch. It is tempting to think that you can then tailor your solution to meet your specific needs, and it must be quicker that way. This thinking is usually proven to be wrong. Industry experience shows that you are more likely to build a best-of-breed solution by using best-of-breed components and concentrating your development effort on those areas where your company can deliver its unique expertise and value to your customers. In today's more cost-sensitive market, you need to spend as little time in development as possible. Therefore, the careful choice of off-the-shelf components is critical to ensure that any solution you build is delivered in a timely and cost-effective manner. The cost of a solution over its lifetime is often overlooked. It is almost always less expensive to buy components, particularly specialist components, instead of building your own. The further away from your core competency you are, the more this makes sense for both you and your customers. As I said before, even for solutions whose primary purpose is not risk management, it is often the case that risk sensitivities are required, or that the portfolio must be revalued under various scenarios. If your aim is to make what-if and scenario analysis straightforward, the ability to revalue a portfolio by simply selecting a different model is a critical capability. By the term model, here we mean an object that represents the set of market data and mathematical model parameters that describe a given scenario. You should be able to revalue the portfolio without having to change any other inputs other than the model object. The ability for your customers to cache, reuse, and transform models of their financial world provides them with the means to perform rapid simulations of large portfolios without the need to reconstruct the model for each trade. A small portfolio of simple vanilla products, or a large mixed portfolio containing complex derivatives in multiple asset classes. Finally, in order to cope, your solutions need to be configurable, grid-enabled, and computationally efficient. Having talked about what makes a good portfolio analysis solution, let's quickly look at some of the components of such a system. First, you need data repositories for data sets such as the trades in the various portfolios and for market data. There might be live market data as well as historical data, depending on the purpose of the solution. Next, there are various architectural components, such as computational servers, grids, web services, data services, and so on. There will be UI components, for example, what I have called a portfolio manager to organize the trade and portfolio data, and reporting tools to present and organize the results of the calculations. The analytics is last but not least. This piece is necessary, but all the other components are also vital for the whole solution. The analytics is a small component from an architectural perspective, but a very high cost component if you build a one-off analytics library from scratch. A recent report from the analyst firm Celent states, "Our findings suggest that firms pursuing in-house efforts for derivatives analytics require an upfront investment of at least $9 million. Moreover, recurring annual costs can range between 25% and 50% of initial investment to keep pricing and risk analytics relevant. This translates to $11 million to $22 million over a 5-year production life cycle to enhance and keep libraries current with ongoing market requirements across multiple asset classes. Aggregated over the total software lifecycle, firms adopting in-house strategies for OTC pricing will require investments between $25 million and $36 million alone to build, maintain, and enhance a complete derivatives library. So we believe that they have the correct order of magnitude based on our in-house experience at FinCAD. We believe that it makes a lot more economic sense for this type of development effort to benefit many systems developers, not just one. That is FinCAD's mission, to make complex finance affordable and widely available. So, as I said before, the analytics is a small component from an architectural perspective, but a very high cost component if you build a one-off analytics library from scratch. Now, at this point, I'm going to hand it over to Carol. We're going to do an audience poll.
So far, we've learned what portfolio level analysis is in the context of this webinar. We've also learned what makes a good portfolio analysis solution. Following poll will help us to gain a better understanding of why you're joining us today and help us walk through the rest of the presentation. Question is, which of the following poses the greatest challenge for you when building a portfolio analysis solution? Requirement specification, system design, market data, analytics development, or analytics integration? Now, I'm sure there are many other things that can be challenges too, but for the sake of this session, let's just look at these 5 and pick the one that you think is the greatest challenge for you or your organization. Let's see how we're doing. Oh, we've got quite a few people voting already. I'm not going to tell you which is leading, although there's definitely an obvious leader here. Just a couple more seconds should do the trick and we'll have some good results for you. So that is, which poses the greatest challenge for you when building a portfolio analysis solution? Looks like, oh no, a few more people are still voting. Okay, I'll give you 2 more seconds. Please get your votes in. Okay, I'd say we have a good result here. And there we go. Requirement specification and market data are neck and neck, with requirement specification being the top issue that we're seeing among the listeners here today. Tony, what do you have to say about that?
Yeah, well, the requirements are sometimes a moving target with a never-ending feedback loop and multiple stakeholders. And market data, well, can be very time-consuming and full of pitfalls, from sourcing it, cleaning it, organizing it, and using it. And then analytics development is also tied with market data. And for sure, analytics development can be challenging and expensive, as the Solent slide showed. Well, that's interesting. I think we'll move on. Thanks for that. So, having placed the analytics piece in the overall context of the various components of a portfolio solution, we will now drill down into the analytics library and ask, what characteristics would enable a portfolio valuation or risk solution to be built efficiently and extended easily? We will be going into the characteristics in each of these 5 areas in the following slides. There are several issues in the area of portfolio specification, which is all about defining the portfolio in terms of its constituent trades and positions. There are no modeling issues here or any analytics. It's just a question of how to represent the trade information on the deal sheets in a form that can be processed by the analytics engine. Firstly, it's important to define a portfolio as a single coherent object. This makes it easy to implement calculations at the portfolio level and operate on the portfolio as easily as if it were a single trade. Every calculation that can be performed at the trade level should be available at the portfolio level. it should be easy to form a portfolio from a collection of trades, or as a union of other portfolios, to an arbitrary level of recursion. It should be easy to support new types of trade within a portfolio system, and the analytics library should enable that. If the analytics library has a trade class, then by creating an instance of a trade with the new type, then all analyses should automatically be available, both at the trade level and also at the portfolio level. This is a very powerful feature, being able to leverage portfolio level calculations for new trade types. The cost of adding support for an extra trade type should decrease for each new trade type that is added. These efficiency gains are possible by taking advantage of the trade infrastructure that would be initially built to support the generic trade class. I myself have been involved in projects to build systems for portfolio level risk analysis and hedge accounting, ones where the effort and cost to add each new trade type was about the same for each trade type, from the first one that was implemented to the last one that was added. This is because the underlying analytics library was more trade-centric, and the market data and model data had to be organized externally to the library, sometimes differently for different trade types. Thirdly, it should be possible to represent any trade. For vanilla trades, there should be templates available to conveniently create them. On the other hand, there should be no restriction on the complexity of trades that can be supported. This can be achieved by using a domain-specific language for trade representation for exotic trades. Finally, it must be possible for a portfolio to contain trades for more than one asset class. For example, it must be possible for a portfolio to contain any mixture of FX trades, equity trades, fixed income, credit derivatives, commodity derivatives, and so on. Such mixed portfolios are common and need analysis. Once the portfolio has been represented, we need to perform some analyses on it, such as calculate its value, its cash flows, its potential future exposure, its value at risk, and so on. It's important that these portfolio level analyses are important within the analytics library, and that the library is not constrained to perform trade level calculations only. If the analytics library were only capable of performing trade level calculations, then these aggregations need to be implemented externally to the library. This is inefficient and sometimes impossible if information about the relationships between the trades is not available. For example, let's look at the sensitivity of a swap portfolio. The first swap in the portfolio is a 5-year swap, 8 million notional, where party A is paying 3-month LIBOR quarterly and receiving 2.4% semi-annually. This swap, in terms of its risk exposure, is almost entirely dependent on the 5-year swap rate, which is quoted in the swap markets. Here's a graph of the value of that swap as a function of the 5-year swap rate. The blue dot is the current value of the swap for the current value of the 5-year swap rate. The slope of that line at the blue dot is the sensitivity of the value of the 5-year swap, is the sensitivity of the value to the 5-year swap rate. Now let's add a second swap to the portfolio, swap 2. This swap is almost a perfect offset to swap 1. However, the notional does not quite match, nor the maturity date or the fixed rate. In swap 2, party A is paying fixed, in contrast to swap 1, in which party A is receiving fixed. So swap 2 is almost offsetting swap 1, but not quite. This portfolio is very idealized, just to get the point across. The brown line is the sensitivity of the value of swap 2 to the 5-year swap rate. Both swaps would also have some sensitivity to other parts of the yield curve, although to a much lesser extent. The value of the portfolio is given by the green dashed line. It is not quite horizontal because there is still some dependency on the 5-year swap rate. The swaps are not exactly offsetting. But how is that sensitivity to be calculated? The value of each swap and the value of the portfolio can be calculated for the current value of the market quote for the 5-year swap rate. That gives the position of the 3 dots. The question is how to calculate the slope of the green dashed line as it passes through the green dot. A common way of calculating the slope is by so-called bumping. You bump the 5-year swap rate up and down by a small amount and recalculate the portfolio, giving the green dots to the left and right. The slope is then obtained by taking the difference in the portfolio value and dividing by the small change in swap rate. Using the right-hand and left-hand dots is more accurate than using a one-sided difference. This is a common approach, but not very efficient. It requires the value of the portfolio to be calculated 3 times altogether, once in the middle to get the current value, and twice more to get the slope. This can be very computationally expensive, especially if model recalibration had been involved. A more efficient analytics library would operate at the portfolio level. It would know the relationships between the trades within that portfolio and automatically be aware of which market data they were exposed to. For example, swap 1 and swap 2 both depend on the 5-year swap rate and not much on anything else. The library would be able to calculate that sensitivity analytically, since it knows all the mathematical operations involved in pricing. In other words, it would be able to calculate the slopes on this chart using calculus, rather than by finite difference or bumping, and without the user having to specify which risk factors to bump. We were talking about the importance of the availability of portfolio-level analyses within the analytics library, and we used first-order risk sensitivity as an example. These ideas are particularly powerful when applied to more complex portfolios, whose pricing requires model calibration. The ability to propagate first-order risk sensitivity to market data through the model calibration process generates huge efficiency savings, compared with bumping the market data and recalibrating the model. Also, if the portfolio-level analysis is performed within the analytics library, then the need for additional external infrastructure to build a portfolio system is reduced. Infrastructure such as external mapping of sensitivities to predefined risk factors or curve points would potentially no longer be necessary. These ideas are also very important when applied to other types of analysis, such as CVA or VAR. These analyses are highly nonlinear, and it's just not possible to derive their values for a portfolio simply by knowing their values for each constituent trade. For example, it's not possible to calculate the CVA for a portfolio just by knowing the CVA for each individual trade in the portfolio, since there may be offsetting positions. The next area is the idea of decoupled trades and models. Separating the concepts of trade, model, and solution method provides many advantages. For example, it's possible to control model risk by substituting different models and solution methodologies. And if the analytics library has a trade or product class, then consistent calculation types will be available on all instruments, leading to more efficient solution implementations. Here's a picture of what I'm talking about. This is a high-level view of a natural approach to separating the concepts. Starting with the product or trade class in the middle, this object represents the financial contract, or a set of trades in the case of a portfolio. This is information that is found on a term sheet or a collection of term sheets. This object knows nothing about quantitative finance. The box on the left represents the model, and here I do not just mean mathematical equations describing the dynamics of certain random variables. It also includes market data and the values of the parameters embedded in the definition of the mathematical model. So here the models: implied rate curves, CDS spreads, default probability curves, or the covariance matrix for forward rates in the LIBOR market model, for example. The gray box on the right represents the solution method. For example, closed form expressions such as the Black-Scholes formula, or Monte Carlo simulation, or backwards evolution, meaning approaches to trees approaches using trees or finite difference methods to solve partial differential equations. This object would also contain the data needed to run these algorithms, such as step size for a grid or the number of Monte Carlo paths to be simulated. Not all solution methods would necessarily be applicable for all combinations of trade and model. For example, for a vanilla European option in the Black-Scholes model, many solution methods would be available, such as closed form, Monte Carlo, or backwards evolution on a finite difference grid or on a tree. However, for exotic trades or for complex models, only Monte Carlo would be available. Once these three objects have been defined and an output request has been formed, then it's just a question of making a call to a single universal function that can process these objects with a single interface. This approach has many advantages. For example, as I said, it's possible to assess model risk by substituting different models and solution methodologies. For the same product/trade object in the middle, which can also represent a whole portfolio, different instances of model and solution method could easily be substituted, and the effect on the value could be quantified. An area related to the previous slide is that of object reuse. For example, since the model object contains the calibrated parameters and market data, then it can be cached and reused for various different portfolios or types of output request. This can represent a huge savings in computational speed, since model calibration is a very computationally intensive step. If new market data became available, it would only be necessary to recalibrate the affected components of the model. Other classes that would benefit greatly from caching and reuse would be curves, market conventions, and portfolio definitions. For example, stress testing a portfolio would be accomplished by setting up the trade object once to represent the portfolio and revaluing it under several different scenarios, each of which would be represented by a different instance of a model. The final set of considerations for the analytics library is in the area of IT. No matter how powerful your analytics platform is, in order to be useful to you and your customers, it must be capable of being deployed into a production environment. Supporting multiple operating systems and deployment options is critical, allowing you to build flexible applications that can be used in your customer's IT infrastructure, regardless of what that might be. You must be able to integrate it into your solutions quickly and easily, while providing a long-term and supportable solution that minimizes the effort and cost required to add new trade and model constructs to your software. Your ability to fully support the solution depends on the support available for the analytics. So, having discussed the attributes of portfolio analysis solutions and of the analytics libraries used to build them, I'll now hand it over to Mark, who will illustrate these ideas with a worked example.
Thank you, Tony. In today's demonstration, I will show you how integrating a modern analytics platform into your applications can reduce the effort required to deliver an effective portfolio analysis tool. I will build the GUI components of my application using Java Swing, and will use FinCAD's new F3 SDK analytics platform to provide the financial calculations needed. I am by no means restricted to using Java for this application. I could have chosen to build my application in C#.NET or C++. The effort required to integrate F3 would have remained more or less the same. In the limited time available, I will not dwell on implementation details, but will, instead, try to highlight the key benefits that Tony raised earlier regarding the use of an analytics library like F3, namely, powerful portfolio specification, the provision of portfolio-level analysis, the decoupling of trades and models, object reuse, and future-proofing. To illustrate these points, I will first walk through a simple portfolio demonstration, loosely based on the offsetting swap example that Tony provided. I've already loaded the application and pre-populated F3 with calibrated market data, as well as 230 or so vanilla instruments that include interest rate swaps, credit default swaps, vanilla options, swaptions, and cash deposits. I will now create a simple portfolio containing just two vanilla interest rate swaps, swap 1 and swap 2. So having created my first swap, I will now use it as the basis for my new portfolio and then add my offsetting swap to the portfolio. The key feature of F3's design, in fact, a key feature of F3's design is the fact that the description of a trade is decoupled from both the construction of the financial model and valuation method used to value it. In F3, the trade description is purely concerned with the terms and conditions specified on the deal or term sheet. Consequently, it is a model-free representation of the financial contract. This decoupling is also true for portfolios. In fact, F3 treats portfolios in exactly the same model-free manner that it handles individual trades. In common with the latest generation of financial analytics libraries, F3 treats a portfolio as a single coherent entity within its object hierarchy. It is important to note here that my application does not know about portfolios. It is the underlying analytics platform that holds the portfolio. The graphical user interface simply references the portfolio by name. On this screen, I use F3's self-describing interface to build a dependency tree for my new portfolio. In this case, we simply have the two swaps I created a moment ago. As you can see, each trade in the portfolio is listed with their independent dependencies. The structure is recursive, and there is no limit to the level of recursion that can be represented. In fact, in this second example, the vanilla portfolio is constructed from 5 sub-portfolios, each of which contains a set of trades. The ability to nest portfolios within portfolios allows us to break even the most complex and large portfolios into more manageable components, and allows for those components to be reused either on their own or as part of other composite portfolios. So having created a portfolio, how do I value and explore its risk sensitivities? Many modern analytics libraries allow you to combine a financial model with the trade or a portfolio of trades and valuation method in a totally generic way to produce calculated output. F3 is no exception to this rule. In this first order risk report tab, I have selected a model called latest market data and calibrations, my new portfolio, and I'm using a default closed form solution to calculate both the value and risk for the portfolio. As I mentioned earlier, this portfolio contains 2 offsetting swaps. I can value and generate a risk report for the individual swaps, or for the portfolio as a whole. In fact, F3 guarantees to be able to generate a risk report for any combination of model, trade, portfolio of trades, and valuation method for which a value can be derived. Let's start by examining the risk sensitivities associated with swap 1. All I have to do is choose the swap by name. Note, I have not changed any other parameters here because the representation of the trade or portfolio is independent of the constructed model and valuation method objects. I am able to pick and choose not only which trade gets values, I'm also free to substitute models and methods also. This flexibility is critical when building applications which will run scenario analyses at the portfolio level. As you can see, F3 calculates first order risk for every market data quote to which this trade is exposed. Let's take a look at the effect of our offsetting swap on the 5-year interest rate quote. The equivalent notional, which is the amount I would have to invest in the quoted instrument to hedge away my exposure to it for swap 1, is in the region of €430,000. But after adding swap 2 to our portfolio, the risk is reduced. to around €7,500. While I know this is a trivial example, I hope it illustrates both the power and flexibility of a good third-party analytics platform can bring to your applications. But what happens if I'm faced with a new instrument type, one that I have never seen before, and for which there is no specific function? In many analytics libraries, you would be forced to either cobble together an approximation of the trade based on individual cash flows and/or other vanilla instruments, or resort to rebuilding your analytics library and possibly even your application too. With today's analytics solutions, of which F3 is a good example, this should not be a major obstacle. F3's approach is to allow you to define custom payoffs for any standard structure. For example, I can take a vanilla interest rate swap and by simply modifying the payoff, create a cap swap. It should go without saying that we can value and manage the risk of this swap as well as add it to any existing portfolio. Ease of integration is a relative term. However, as a former software developer and solution architect, it's a subject that is actually truly close to my heart. In this example, I have used the Java API provided by the F3 SDK and have chosen to embed a single instance of the library into my application. Therefore, I have wrapped F3 in a singleton class that loads the library and manages all of the calls to it. A key feature of F3 is that I was able to build my entire interface using fewer than 20 lines of F3 specific code. In this case, I've enabled two of F3's API calling styles. The low-level API relies on passing in an XML representation of the F3 function call I wish to make. As an aside, these packed XML calls also make the ideal message payload for message-oriented middleware solutions. The second API implemented takes two arguments, the name of the function to call and a hash map of key value pairs representing the function arguments. F3 also supports direct or explicit calls to its API. But in the interest of time, I have not shown this call style here. In this short demonstration, I hope that I've been able to give you a flavor of how using a modern, flexible analytics platform can accelerate the delivery of your applications, and have also illustrated the benefits of having a library that provides powerful portfolio specification combined with the provision of portfolio-level analysis, and how a fully decoupled trade and model representation lends itself to object reuse and provides the flexibility that gives a future-proof solution. At this point, I will hand over to Carol, who will take us through our Q&A session.
As you've seen from Mark's short demo, by utilizing an analytics library that met the criteria outlined earlier in the webinar, he was able to efficiently develop a small yet highly flexible portfolio analysis solution. The solution by design would then be easy to maintain, extend, and scale for both simple, complex, sizable, or dynamic portfolios. I'd like to now open the floor for your questions. I encourage you to again refer to the right-hand side of your screen and just type your questions into the question box in the GoToWebinar side, and we'll go from there. First of all, I would like to remind you that the recording of the webinar will be made available to you. You'll receive a follow-up email, probably in the next couple of days, and then you can go in and view the webinar, share it with your colleagues as you wish. Also, with regards to the poll, one thing I failed to mention when we were running the poll is we got a 73% response to that poll. Now, going forward to our questions. Let's see here. Here's one. How can you output, or can you output DV01 across different asset classes for a whole portfolio?
Yes, one of the characteristics I discussed was decoupling the trade and model concepts and providing consistent calculation types, including DV01, on all instruments. So by extension, on a cross-asset class portfolio, this is also possible.
Thank you, Tony. Here's one for Mark. Parallel computation using the library calls is the question.
Okay, if I understand this question correctly, I believe what you're asking us is it possible to make parallel calls or make calculations in parallel using F3? The answer is yes. By design, F3 is grid-enabled out of the box, which means that any simulation type calculation can be made and distributed across a grid. F3 is also thread safe and multi-threaded, and therefore you are actually able, if you build your application appropriately, to parallel process calculations and run multiple calculations simultaneously.
Thank you, Mark. And here is another one for Tony. How is it possible to calculate first-order sensitivity of the portfolio value to the market data without bumping?
Well, so the pricing algorithm knows what series of mathematical operations is required for the valuation. So at the same time, there's a corresponding mathematical algorithm to compute the sensitivity of the outputs with respect to the inputs. So as long as the detailed calculations are sort of woven into the fabric of the infrastructure, then the first order sensitivity can be calculated at the same time as the value with little performance overhead. This is true even for Monte Carlo based prices and also for model calibration. So the calibration that involves minimizing goodness of fit metric. This is very powerful since the first order sensitivity of the portfolio to the market data used to calibrate the model can also be calculated.
Thank you, Tony. Let's see. We've got a number of questions here. Here's one for Mark. Could you elaborate on real-time or near real-time capabilities? Mark?
Certainly. F3 is designed as a highly computationally efficient library. We rely heavily on lazy evaluation, so F3 only calculates the values it needs to calculate as and when it needs them. So it is intended to be a real-time system and intended to be deployed in real-time or near real-time environments. The performance capabilities of F3 are actually, we believe, are amongst the best on the market. And when it comes to pure real-time processing, obviously depending on the calculation you're performing, certainly for closed-form solutions, F3 is definitely a real-time solution.
Looks like I've got another Mark question here. Do you support GPU compute engines like AMD Fusion, for example?
Currently, F3 does not support GPU directly. This is actually a project that's in hand and will be delivered in a future release of F3.
Thank you, Mark. Okay, let's see. Tony, perhaps you can take this one. What types of portfolio level analysis is FinCAD getting requests for most recently?
Well, since the crisis of 2008, we're getting a lot of requests for calculations related to counterparty credit risk, such as credit value adjustment and potential future exposure, to be included in our libraries. Also, first order risk and stress testing are common requirements for risk systems.
Thank you, Tony. Okay, let me just scan through the questions that are here. I've got a few other ones yet. Quite a few questions have come in. Let's see. What trade types do you support? That would be, who wants that one? Tony, would you like that question?
Well, basically we support all trade types. The question is, in terms of dedicated, convenient functions to create instances of those trades, is a set of trades that's we're expanding all the time. But there's no limit to the complexity of the trade that can be represented in F3 because of the use of a trade representation language. So yeah, no limit.
Okay, I've got time for one more question here. And here's one for Mark. How can you need only 20 lines of code to do what you were showing us today?
Fundamentally, it was a design choice in the implementation. Because of F3's generic and very lightweight APIs, to implement your interface to F3 requires, you can do it in fewer than 10 lines of code. In truth, I've used about 20 lines because I used multiple calling APIs. If you use the pure XML in and out representations, then having written a singleton class that accepts an XML string as a call and can process the XML return from F3, you never have to write another line of actual F3 code in your library. You can manage all of your calls to F3 using just XML strings and string representations of structures built in F3. F3 also provides the ability to generate those calls in Impact XML using either the F3 Excel edition or, as of May, the F3 MATLAB edition.
Now, I said one more question, but I notice here that there are a few questions that overlap a bit, and the key topic there seems to be, how does the FinCAD solution integrate with other vendor solutions? And I think that's something that we could give just a high-level response to.
So it depends really what you mean by integrate with other vendor solutions and what those solutions actually are. If we're talking about integrating into order management systems, trade processing systems, etc., then that would be definitely that's a relatively straightforward process. I mean, I'm not trivializing it because, I've made a career of doing exactly that kind of work for 15 years, and it's not easy. But F3 is designed with it has different. We have different levels of APIs. We have the ability to structure those calls in a way that suits whatever calling paradigm your integration requires. And it also happens, that F3 lends itself to both loose and tight coupling. So you can loosely, if you go for if you're working in a service-oriented architecture, then using the XML in and out type approach, F3 it's a straightforward task to build an SOA adapter to using F3 that will allow you to convert those calls in and out. An example of that, in a real-world example, is one of our early adopters relies heavily on Lexife's ML3 trade description language, and have integrated F3 by simply writing an XLCLT adapter which converts Lexife's ML3 trade description language into a form that F3 can take, that F3 represents. And in doing so, we're now able to load any trade into F3.
Thank you, Mark. We have reached the end of our time, and I see that there are a number of questions that we've not been able to respond to. What we will do is compile responses and get back to you with those. Thank you for joining us today. Please note the contact details on your screen. If you have any further questions or would like to see a customized demo specifically for your company, please get in touch with us. There's a form you can fill out on the website, or you can give us a call. Either way works. And watch your email inbox over the next couple of days for a note giving you access to the recording of this webinar so that you can share it with your colleagues or review it again as you so desire. Again, thank you for joining us, and we wish you all a good day.